now we can launch into our panel discussion. And what I'm going to do here is I'm going to scroll a little bit through our chat history because there are quite a few questions that have been posted. But if you want to ask something different, or if you want to ask a broader question to several of the panel members here, please do raise your hand. I see this here. And we're going to scroll. We start with this one. Yeah, Dan has a point for now. Please, Dan.
Hey, good morning. So this is a question for Tyler that I didn't get to ask before, and perhaps it's for the panel as a whole, but I think it's mostly for Tyler. So your discussion of this gap reminded me of another gap that we've discussed a lot during the KITP program, and that's the Exoplanet Radius Gap. And one of the big discussion points, and I think already last year, but perhaps more so over the last year since the program, was whether the gap is empty. So basically, it has to do with the fact of how quickly do objects, in this case planets, move across the gap, so from one peak to the other. And I wonder whether a similar, and so different theories predict different timescales of how quickly that might happen, and hence make different predictions as to whether we should actually find any planets, or in your case stars, in this feature that you see in this gap. So I wonder whether this is a similar, whether you thought about a similar argument for the gap in the rotation period plane. In other words, can you make any arguments for the stalled spin-down model as to how quickly this should happen? And can basically the points within the gaps, because you have, it's not very clean. You have a few data points that are in there, and presumably you can check whether the periods that you measure are reliable. So can the rotation period measurements in the gap tell you something about the physical mechanism that's actually causing it? Or in other words, is it consistent to see a few if it's really stalled spin down that's causing it, rather than some other theory?
Yeah, that's something that I haven't done yet, that I have been very interested in doing, actually, is looking at the specific stars within that gap to see if there's anything that we can glean from that about, like, yeah, what might those stars be doing right now if those are actually well-measured rotation periods. But I don't really know the answer to the rest of that question, I guess. My understanding of this sort of stalled spin-down model is that once the envelope becomes decoupled from the core, it would resume sort of a smooth spin-down. So I would think that it wouldn't be, a very instantaneous jump. But I don't know, and I think that's a really interesting question and definitely something to pursue. Yeah.
Oh. So next, I would like to take Jim's question, and after that, we move on to Pierre's question that he posted in the chat.
Yeah, I just wanted to follow up on that. I think that's a really great point, Dan, because that is one of the predictions of the model, is how many stars are in that gap. So that's something that should be tested. I personally am a bit skeptical of that model because those are very long for envelope decoupling times. And physically, I think it would be hard to reconcile that with what we see in post-main sequence stars, which is that those 4 envelope coupling timescales are shorter than we thought. So it's a little hard to explain both at the same time. So anyway, this would be a nice new test of that model.
Right, then Pierre, you wanted to ask something.
Yes, so this is a question for Amoa about her talk, but also I need input. To ask the question correctly, I need input from people who know about radius inflation and stellar models. So I've come across this faint young sun problem, which is fascinating. If you were to look at the sun 2 billion years ago and look at the Earth, if you don't draw your habitable zone right, you would conclude that the Earth was not habitable 2 billion years ago. And that's just because of stellar evolution. The sun was about 70% fainter 2 billion years ago, but we know we have marine fossils. I hope I have the age exactly right, but it's about 2 to 3 billion years ago. So there's this really interesting question about what did the sun look like 2 to 3 billion years ago when we know there was life on Earth, but the sun was 70% less luminous. And that's obviously something to do with like the atmospheric properties of the Earth and heating and so on. But really my question was what sort of models of the sun are people using to explore that? Because I think if you take the properties of the convection on the sun now, and use that to extrapolate back a model of the sun, you'll get some property, right? I don't know exactly, but the luminosity, it will predict a particular temperature. But if the radius inflation thing happens to the sun, let's assume that the sun was more active, more rapidly rotating, maybe its radius 2 billion years ago was, I don't know, 5%, 10% bigger than your standard solar model would predict. Maybe the sun, when it was younger, more rapidly rotating, more magnetically active, maybe this radius inflation was puffing it up. It doesn't affect the luminosity a lot, but it would drop the effective temperature. So really, I suppose the question is, how sensitive are climate models for the Earth 2 billion years ago to the input SED, or the assumed temperature of the sun? And if you dropped it by 50, 100 Kelvin, would that give you interesting effects in this faint young sun problem? Mm-hmm. And actually, am I right in thinking it is maybe about 50 or 100 Kelvin? Sorry, that's a complicated question, but it's a complicated topic.
Yeah, I think it's what, 10% per billion years. So I think you're at 70% about 2 to 3 billion years ago is correct. Benjamin Charnay has done some studies with climate models looking at trying to solve this faint young sun paradox. And I think there's been some work even before that by Casting et al. And it is this, like, you know, it's the paradox. If we know that the sun was a lot less luminous back then, how were we not completely frozen over? It's still an area of active research. But I think that if I think about Snowball Earth, which has its own kind of paradox, that we believe that Snowball Earth 600 and 800 million years ago occurred, that there's geomagnetic evidence, paleomagnetic evidence that shows that indeed we had extensive, if not global, ice cover from pole to pole, and yet we know life survived. We have evidence that even photosynthetic life survived. Then it brings the question of perhaps it wasn't a full snowball, perhaps we didn't have thick, 1 kilometer thick by thick ice sheets, as some people like Steve Warren have proposed. Some people, so Steve has said that the stable solution, the only stable solution, is kilometer thick ice. But then you have people like Chris McKay who say, no, you can have a thin ice solution. And that is extremely model dependent. So there's all these papers, there's sort of this back and forth about 15, 20 years ago about this whole property. And it's by extension, Europa. We can talk about that too. Is the ice kilometer thick ice or thin ice? You know, it's very applicable to those studies as well. But even if you had extensive ice everywhere, there's people have been talking about refugia, areas around tropical islands and things where there perhaps wasn't any ice, where you could have photosynthetic life having access to incoming stellar radiation. So I don't have any definitive answers for you, but I think that those others have tried to simulate this faint young sun in climate models, and people have proposed things like methane as a potential, the atmospheric concentration itself, and pinpointing that atmospheric composition back at the time of the 70% fainter, 30% fainter sun, as a possible way to mitigate against the freezing temperatures that would have ensued.
Right. I would have a follow-up question actually for our Mauer. So earlier on, when there was a question about stellar winds and activity, you said that currently these climate models don't explicitly include the activity effects. Now I'm wondering, especially for the low mass M dwarfs, when they flare, the amplitude of the flare in basically the bolometric band can be quite large, like it can even rise by a factor of 100% or so. Is that actually of an order, if that happens every few days or so, that actually could make a difference in these climate models, or is that an effect that would sort of average out and wouldn't make a big difference?
Yes. So these are areas where people are working and have worked in the last 10 years to address the effects of highly active M dwarfs on habitability, the habitability of orbiting planets. This is one of the biggest concerns we have, is that although M dwarf stars have pose a lot of advantages in terms of looking for habitable planets, you know, they're the bulk of the stars in the galaxy. It's easier to detect them with transits and RV, you know, that they have these long stellar lifetimes, so they offer plenty of time for life to evolve and develop. However, because of these long lifetimes, right, they're active for a long time, on the order of 1 billion years, and that's just right at the point when life is starting to evolve. We think that life took 500 million to 1 billion years to get a foothold on the Earth, and that's the point when M dwarfs are particularly active in their cycles. And so even with that, even if we didn't do anything to address that, you could still have life at the bottom of the ocean, where it wouldn't be exposed to that intense X-UV radiation. So that, you know, that allows us to say, well, it's not a make or break for habitability. However, because we're also talking about how to identify that life, if the life's at the bottom of the deep ocean, it's not really going to make any difference in terms of being able to detect it. Life has to be walking around, swimming, you know, on the surface, so that we can, so that it can make its presence known in ways that we could observe remotely, like in the form of biosignatures. So people like Antigonus Aguirre and others have papers where they've used photochemical models, so 1D photochemical models, which, you know, would allow you to explore the effects of high energy radiation on an ozone layer, for example. And what they've shown is that if you don't include kind of the CME events or the proton flux that can accompany CME events, then your ozone layer can remain largely intact. However, if you do include the proton flux events that can often accompany CMEs, then you can deplete your ozone layer by as much as 90-something%. And so it could indeed be a factor, because ozone, of course, on the Earth helps protect us from harmful UV radiation, which would be very biologically damaging to surface life. So, but currently there really isn't a model. People are working on it. This kind of one model that rules them all, where you have the photochemical code coupled to the climate, to the 3D climate code. There are some codes like VPlanet that are trying to couple a number of things together, of course, because you have, you know, plate tectonics and dynamics, orbital dynamics, and all these things that are incredibly important for climate too. And also people who are in space weather and upper atmosphere stellar interactions, planetary upper atmosphere stellar interactions, are working to combine and couple many of their codes to the planetary atmosphere codes, because this property, the high energy radiation and its effects on atmospheric evolution and atmospheric retention in general for very close planets, these are important effects that have to be quantified, because they will make a huge difference in a planet's ability to sustain its atmosphere, and as a result, life on the planet itself. Yeah.
Yes, thank you. I would like to go back to a question from the chat. This was a question for Adam. So there was a question by Julian Alvarado Gomez, and the question was, if you reduce the degrees of freedom, for example, not take into account the radial shear, how much latitudinal shear would you then get?
Sure. So I was thinking a bit more about this one, and I can sort of answer it by going at the sort of correlations between the radial shear and the latitudinal shear. And it looks like the answer is that we don't get much more. Maybe it's 50% more, but still probably consistent with 0. Now that's at the shortest period window. So maybe the answer is different at longer periods. We sort of, I guess we didn't think about doing that type of analysis, mostly because we expect there to be radial shear, just sort of thinking in terms of the sun. But I think it is a good idea to try. So I'll go back and see.
Great, thank you. Then I would like to scrolling through the questions. We have a few questions that I think would be interesting to address here again. We have a question from earlier from Janie Tayar for Tyler, and this is about the cluster tracks that you basically see where the cluster stars fall, does the factor that the cluster pileup is not at the same place as the lower edge of the gap, does that mean that there are two unrelated issues in these physics of the spin down?
Yeah, it very well might. I haven't thought a ton about that, but you're right. The pileup is distinctly not at the location of the lower edge of the gap. I think it probably has to do with the exact shape of those gyrocones. As we get to later times, how exactly does like the morphology of that little ripple make its way through that plot? Something maybe related to that I didn't super mention in my talk but could note now is that the lower edge of that gap is much more sharp and well-defined than the upper edges. So I think that might have bearing on the processes that are going on there, but haven't really investigated that in any depth.
Right. And we have a quick follow-up question from Lynn Hillenbrand just now on the chat. And this is, how much are your results on rotation gap limited by using the Gaia BP minus RP colors instead of, for example, using infrared colors so that you could get farther into the M spectrotypes?
Yeah, I'm not totally sure about the answer to that. I don't know how much our results are limited by that. I do know that the major limit when moving further into the M spectral types is just what we have in the K2 data, and things start to get really dim out that way, and that means that we're seeing a much smaller amplitude of variability, especially compared to the shot noise. So that's kind of what sets the limit in terms of how far we get out into the infrared.
Okay, thank you. Let's see, are there other hands-up signatures from our attendees and or panelists? We have a few more questions in the chat, but if we not get through all of them, I would encourage people very much to go also into the Slack workspace and ping the people directly where you want to ask more. I would like to close with a question to all of our three panelists looking into the future. So if we go sort of in reverse chronological order from Adam over Ao, Mawa to Tyler, if you could wish for a certain observing mission or observing capabilities, or even in terms of modeling, what would be on your wish list to make the next step forward in your research that you have presented here today?
So I'd love to have really good rotation rates for eclipsing binaries with error bars on them. I'm not exactly sure what that looks like in terms of the mission, but that would probably be the big one. Also for giants, so this sort of analysis gets much more sensitive the bigger your convective envelope. And so for giants, we can be much more sensitive, but we could only find a few giants that we were convinced were synchronized, and that's not enough. So a bigger sample of those would be great.
Okay, thank you.
Just a quick comment on that.
Oh,
if you take a giant and spin it up, it tends to produce a lot of mass loss, and you get RS can-bend type activity. I'm just wondering if you start throwing mass off the surface, is that going to mess up your analysis?
As long as we're not actively throwing it off at the same time, right? Like if it was thrown off in the past, that's fine. If we're currently throwing it off, then maybe we're in trouble. But it would depend on the time scale.
Okay, thanks. Then Ao Mawa, please.
I would love to see one of the next generation mission concepts go through and like LUVOIR or HABEX, these missions that are very ambitious, but that have a chance at perhaps not only resolving the atmospheres of smaller Earth-like planets, Earth-sized planets, but perhaps getting surface composition information. We've shown from simulations that using at least the LUVOIR model that you can discern and break degeneracies between surface compositions with LUVOIR. And so I'd love to see one of those missions fly.
Thank you. Tyler.
Let's see. I mean, I'm just a huge fan of these like time domain missions, so I would love to see you know, a time domain mission with longer baselines so that we can get more accurate rotation periods as we get up towards the top of that gap. Also, yeah, longer baselines, higher precision, and ideally multiple wavelengths. I think that would really help us to see exactly what these stars are doing as they rotate.
Yes, thank you very much. So yeah, we have lots of cool things to look forward to, and to submit a long wish list to NASA and ESA and other agencies. Thank you everyone for your participation here today. It was a very interesting first day we had in the program. If your question that you had for any of the speakers from the chat didn't get answered, or you just came up with a new question, please move over to the Slack channel where you can ask the people directly. You can also discuss in the, what's it called, reunion channel on that workspace. Discuss general things there in more detail if you like. And we will meet again tomorrow at the same time using your either panelist or attendee links. Yeah, any final things from you, Victor? Did I forget anything?
No, just to say that if people have not yet received, I mean, you should receive an email today with the link to join the Slack channel if you haven't joined it yet. So that will come from KITP hopefully later today.
Very good. Okay, thanks everyone. Have a very nice morning, afternoon, evening, or night, depending on where you are, and see you all tomorrow. Bye.